Thank you very much for the introduction, and thank you, Shane, for inviting me here to speak. Can you hear me okay? Is that great? Good. So my name is Jack Harvie-Clark, and as a firm of acoustic consultants, we undertake acoustic design in all sorts of rooms, but we do quite a lot of schools, and we've been involved in reviewing the acoustic performance standards for schools that Adrian was talking about this morning. And so we asked the question, what is the right reverberation time and why for a classroom? And we've found that these concepts of clarity and strength are very useful for asking those questions and also applying to many other situations. So I'll try and explain a bit about why we might want to consider them and how we use them. So going back 2 steps, when we do the acoustic design for a space, we're concerned with we should be concerned with the acoustic requirements of the users, not just meeting the performance requirements that are prescribed. So the obvious thing that users need in the classroom, for example, is speech intelligibility. They need to be able to hear what's being said. We know that controlling the background noise is very important, and that relates to the building services, but probably more importantly, to the noise generated within the room. How do we explain that? How do we quantify how that's going to be affected by the room acoustic response? Something which we think about less often is the acoustic comfort of the talker when we don't have the benefit of microphones. So this is going to be a bit techie, so I'm sorry for all the non-acousticians in the room. Obviously, for rooms, the primary acoustic or physical descriptor is reverberation time. But this is really a descriptor of the room physical response rather than correlated with what users actually want. We have STI, and it was great to see the equations there in the last presentation, because that shows you how complicated STI is. So trying to understand the influence of one thing or another on the STI parameter by design is very complicated. And it also mixes up the room acoustic response with the background noise in one parameter. So we can't separate out the effect of the background noise on the room acoustic effect when we're trying to think of speech intelligibility if we use STI. So this is partly why clarity is so useful. So what I'm going to talk about then is very briefly Barron's revised theory for the spatial decay of the reverberant sound field in a diffuse field, from which we can derive very simple models for strength and clarity. And part of their usefulness is their simplicity. Because then we can think about what design considerations we're interested in, the user's acoustic requirements, and the effect of these parameters on them. I'll then show you a sophisticated model for classrooms that shows just how far we can take these concepts, or that other people can take these concepts. And then ask the question, what about in non-diffuse spaces? How useful are the simple models? What can they tell us? And I hope all the way through, I'll remember to remind you about how these concepts can be applied to new situations. So when we come to design situations for which there are no acoustic performance criteria, what do we do? Where do we start? How do we start thinking about the acoustic needs of the users? So very briefly then, Barron's revised theory, and there's a reference to his paper down there that was published in JASA earlier this year, because I'd love to talk for longer about this, but I won't have time to tell you about the other things if I do. But this is the key assumption in it, I think, that reflected energy only arrives from the moment after the direct sound arrives. So that means this is his figure 2 from his graph, which you want to have a look at. This is a reverse time integrated impulse response. And 3 positions, A, B, C, are to increasing distances from the source. And I'll give you an explanation afterwards if you're interested as to how this explains the spatial variation in the reverberant sound field. So strength, simply defined like that. We know the direct sound is described like that, and we'll use a value of Q of 1 from here on. So it's a function of the distance between the source and the receiver. In classical theory, we might describe the reverberant field like that, but with the substitution of the Eyring equation for reverberation time in Barron's theory, we get this expression for the reverberant sound field. So the reverberant sound is a function of the distance and the mean absorption coefficient, as well as the sound absorption in the room. So all we need to know is the room dimensions, the surface finishes, and we can calculate the spatial variation of strength, simply like that. So it's all about how loud is a sound in a room, which is mostly what we're interested in, or often, rather than how quickly the sound decays in a room. So we use that expression for strength to calculate clarity in just the same way, a very simple expression. So it's the difference between, defined as the difference between the early and the late arriving energy. So it's a bit like a signal to noise ratio. Well, it is a signal to noise ratio, really. The early part being containing the signal, the late parts being the noise. Because we're assuming diffuse field conditions, we can integrate from 50 milliseconds to infinity to calculate the fraction of the reverberant sound that arrives late, and the other part arrives early, along with the direct sound. So we have a simple expression, again, just based on the physical characteristics of the room and the distance between the source and the receiver for clarity or intelligibility. There's another parameter that takes on from there called U50, or the unfavorable ratio, where background noise, or the noise generated within the room, is added into the late arriving energy. So how do we characterize rooms then? And as Trevor mentioned earlier this morning, usually we're not so interested in the speech intelligibility for the person who's close to the talker. We're interested in what are the conditions like for the person at the back of the room. So if we set the distance between the source and the receiver to be the length of the longest side of the room, what we find is that clarity is independent of room size and is only a function of reverberation time for the normal sorts of reverberation times that we get in rooms. So we get a graph like this. Marshall has given us 4 octave band coefficients to correlate clarity with speech intelligibility and STI from 500 hertz to 4 kilohertz. So the 3 values of clarity that I pick out, 0, 3, and 6 dB, correspond to or correlate with an STI of 0.5, 0.6, and 0.7. And this shows that we can achieve those when the talker and the speaker are at opposite sides of the room with reverberation times of 0.65 and 0.45 seconds. So this is calculating speech intelligibility without any of those complicated expressions for STI. There is a diffuse field assumption in there. If we take then let's say that we adopt a target for speech intelligibility for the person at the back of 3 dB, what does this mean as our room size changes? Well, we know that the reverberation time will need to stay the same, so we can see that as the room gets bigger, the mean absorption coefficient will need to increase to accommodate that. So that might get to a point where it's not actually practical to achieve that level of sound absorption, or desirable, because clarity is only one aspect of speech intelligibility. And I'll come back to that later. But if we take the concept of communicating over a fixed distance, let's pick, for example, 10 meters in sports halls, and let's say we'll accept a value of C50 of 0 dB, then what we find is, as the room gets bigger, the mean absorption coefficient stays the same, and the reverberation time increases. I didn't know we were going to hear about the revision to DIN 18041 this morning, but the lines there are based on these mean absorption coefficients, and I think in the old standard they're based on 0.19 and 0.23 for the different classes. So this is a good way, I think, of determining what's the appropriate reverberation time to correlate it with the volume of the room, but really it's the mean absorption coefficient that we're designing around when we do that. So going back to the classroom, and Bradley tells us how important signal-to-noise ratios are. Strngth tells us immediately about signal-to-noise ratios. So if we know that someone is talking with a normal voice of 60 dB at 1 meter, and the background noise is 40 dB, then we know we need a strength of 15 dB to get a signal-to-noise ratio of 15 dB. So this graph shows the minimum reverberation time with room area to get a value of strength of 15 dB at the back of the room. So obviously, as the room gets bigger, you need more reinforcement from the room to achieve that signal level. We also know that we have a limit on the reverberation time of 0.65 seconds to achieve a certain level of clarity. So we can split up and consider those two aspects of speech intelligibility separately, the clarity and the signal-to-noise ratio. So the shaded area, if you can see that it's shaded, shows the design area that meets both these criteria. So this graph immediately shows us that we can't design a room that's more than 85 square meters, where somebody can talk with a normal voice at the front and someone can hear with good intelligibility at the back. We also know that limiting room gains from the people in the room is perhaps even the most important aspect of classroom acoustic design from the Essex study. And so maybe we want to design right as far close to the blue line as we can for different room sizes. When we define strength as the difference between so when the distance between the source and the receiver are the length of the side of the room away, what we find when we reduce the reverberation time is we get there's a nonlinear relationship. So when you reduce the reverberation time from 0.8 seconds to 0.4, the reduction in strength is 6 dB. So with classical theory considerations, we might think if we halved the reverberation time, we would reduce something by 3 dB. But if we think about strength in this way, we can see the effect on reducing the noise levels. And many times today we've heard about noise levels in different situations and how the background noise from the people in the room is one of the most important aspects, and how do we design that soundscape. So this is a very simple way that we can do it and get insight into the effect of the absorption in the room. We can also use the concepts of signal-to-noise ratio in open plan spaces to design for negative signal-to-noise ratios where you don't want to have intelligibility of the speech. And the concept of strength is already in the parameters of ISO 3382 Part 3. The speech level at 4 meters, that's just strength with a speech spectrum. And DL2 is the spatial decay of strength. So these concepts are there. We just don't necessarily call them that. So a more sophisticated model to show what can be done then with these very simple considerations that was presented a year ago, based on the U50 then favourable ratio. So the student background noise, the noise from the students is included as background noise, and it's a function of the number of students and the amount of absorption in the room. So the more people you put in a room, the more background noise they make. So the teacher's voice level responds to that with a Lombard effect. The teacher raises their voice to take account of the noise level generated by the students. The limits of vocal comfort for the talker are included as constraints in the model so that it can't all increase incessantly. And also the room acoustic response for which, in the range for which there is acoustic comfort for the talker. And he also uses a listener distance of the average room dimension. And for that he produces graphs that we wouldn't necessarily anticipate that look like this. So to achieve a minimum value of U50 for 1.5 dB, which would also correspond to an STI of 0.6, this is the range of volumes with reverberation time for a different number of people in the room. So we might have anticipated that if you put more people in the room, you would need a lower reverberation time, but we wouldn't necessarily anticipate it, I don't think, that you would be better off in a smaller room with more people. That's probably due to the contribution of the direct sound. Also, significantly, nowhere on this graph is there a design range for 30 people in the room, which is the normal condition in England, I'm sure many other countries as well. So we can't get, if the assumptions that go into the model are correct, we can't get that level of intelligibility, an STI of 0.6 for the person at the back, when there's 30 children in the room, or people. It also suggests that reverberation time we have in England for secondary schools of 0.8 seconds is almost certainly too high, and that we probably need a minimum reverberation time to prevent rooms being too dead. It's very unlikely to happen given the finance for schools in the UK. But there is a small possibility that of that happening. So what happens in non-diffuse fields then? So I'll present some measurements from a sports hall and some from a classroom. So we'll look at the spatial decay in a sports hall and spatially averaged measurements in a classroom. So this is a typical forecourt sports hall in the UK. There's a line of absorbent panels at a fairly high level and an absorbent soffit. So we measure a mid-frequency reverberation time of 2.6 seconds when we would calculate 1.9. So with the measured results in green and the predicted in red, pretty good, just from a very simple back-of-the-envelope calculation. So you might even struggle to do that with a cat model. Looking at C50 is also well predicted with this very simple model in this room. And the yellow trace there shows STI on the right-hand side, which is also well correlated with the weighted C50, reasonably well, I would say. It's a slightly different measure. So that looks surprisingly convincing. In a classroom, I'm going to show you the opposite, well, partly the opposite thing. Looking at spatially averaged measurements on the opposite side of the room, so thinking of the most adverse conditions, and we get these types of results for reverberation time. So in the high frequencies, the measured values in green significantly higher than what we would predict in red. And we all know about the grazing sound field and non-grazing sound field. Some of us, sorry. Strength, however, and we find this in all our measurements, correlates with the amount of absorption in the room and not the reverberation time. So it turns out that reverberation time is a poor descriptor for loudness in the room, and we're actually better at determining it from the amount of absorption in the room. And we found this in all our measurements in sports halls and classrooms that we've done. So I think this theory probably is only valid for spaces of simple shapes. As Trevor mentioned this morning, if there's many ribs, then that will cause a decrease in strength towards the back of the room. When we look at clarity in there, however, we find that the predicted values with the simple theory in the red line significantly overpredict what we measure, and clarity in this room is very well predicted by the measured reverberation time using the same theory. We usually find it somewhere in between. So does this mean that the diffuse field models for clarity are no good? Well, I think, and I'd be very interested to hear what anyone else here thinks, that the predicted value with the diffuse field model is as high as it can possibly be. So I don't think we can do any better than that. So if our diffuse field model shows a constraint for clarity, we at least need to achieve those conditions. Any defect or any non-diffuseness in the sound field, which means the actual reverberation time is longer than we would calculate, means I think that the values of clarity will always be lower than we would predict. To conclude then, they're very simple models. We can understand the effect of any of the parameters on them. And we can understand that because they are associated very directly with users' needs about background noise, about loudness, speech intelligibility, we can understand they're very useful tools to when we come to new situations, we can use them to reevaluate the conditions we might need in the classroom, and we can also use them in new situations to understand what the user's acoustic needs might be and translate those directly into room characteristics. As I mentioned, strength correlates well in non-diffuse fields. This also means when we use things like reverberation time to correct a sound insulation measurement, we're overestimating the sound insulation by the difference between the predicted level and the... Sorry, I'll go back to this slide briefly, but the difference there between the yellow dotted line and the green line shows the difference between effectively the relationship between sound power and sound pressure that we're measuring with the reverberation time compared to what is actually there with the green line when we measure strength. So we might be over-predicting the sound insulation in the higher frequencies by 3 or 4 dB in that room. predicting clarity in non-diffuse fields obviously requires further work, and I'm looking forward to Erling Nielsen's talk tomorrow morning to try and understand that better. Thank you very much for listening.